So the title of my talk is What is and is not a planet? And at face value, that might seem very pedantic. After all, we're just talking about the definition of a few letters, a few words, not necessarily the intrinsic properties scientifically of this concept. But as I'll show, the concept of what is and is not a planet has led to very deep understanding of the formation of these objects, both in our own solar system, as I'll start out talking about, and then in the objects that have now been discovered around stars like the Sun, other stars like the Sun in our own galaxy. And so this question has also troubled astronomers for more than 2,000 years. If we were to go back and to listen in on the debates of ancient Greek astronomers, there would be debates about what things they saw in the sky should be considered planets and what things should not be considered planets. And that question has continued more or less to this day. So if we were to go back in time and ask an ancient astronomer what they meant when they said a planet, they would refer to some subset of these things pictured right here. So this is a picture from the night sky about a year ago when the 5 naked eye solar system planets, that is Mercury, Venus, Mars, Jupiter, and Saturn, were all visible in the night sky all at one time. Now, to some Greek astronomers, this was all the planets there were. Other Greek astronomers, though, also included the so-called luminous planets, that is, the moon and the sun. So even then, there was a debate. They all agreed that the things that they called planets were things that moved in the sky relative to the fixed stars. But even which things that moved in the sky should count as planets was something that was debated. So now if I give the modern take on that ancient understanding, here I plotted on a log scale the distance from the sun in AU, that is the average Earth-Sun distance, and the mass of these objects in units of Earth masses on the y-axis. This is what the 5 ancient planets, that is Mercury, Venus, Earth, Mars, Jupiter, and Saturn, would look like. Now that was the understanding for a long time when the director of the Bath Orchestra and a talented amateur astronomer and telescope maker discovered something new. So at 10:30 p.m. on Tuesday, March 13th, 1781, this astronomer, William Herschel, who was engaged in a search for visual binary stars, that is, stars close together in the sky that moved in such a way that they might be gravitationally connected, saw something that he hadn't expected to see. Now, he was focused on this search for astrometric binary stars, so he didn't come back to this field until 4 days later. So at 11 p.m. on Saturday night, March 17th, he was surprised to see this object had moved. People knew that objects like that moved, and they called them comets. But comets typically had a different appearance in his telescope. They looked fuzzy, whereas this thing looked just like a disk. And comets also moved in a different way. This thing appeared to move very slowly, and it moved in a very regular way, whereas comets would have moved quickly and kind of in irregular ways, representative of a qualitatively different orbit. In fact, he initially thought this new discovery was a comet. But as he raised the alarm and other astronomers started looking at it more closely, it was clear to see that this thing was different. It was something that had been different than anything which had been discovered since those ancient astronomers looked up at the night sky. And in fact, within a few months, people understood that this thing was a new planet in our own solar system, eventually known as Uranus. Now, as a reward for discovering this new planet in the solar system, which is a phenomenal achievement, very few people in the history of humanity have had such an honor, he got an offer to become astronomer to the king at a salary of £200 per year. Now, I went back and looked at the Royal Bank of England's official inflation calculator to see how much that would be today. And it turns out that's about $37,000 per year. So this is someone who had done something that no one since the ancients had done, was hired to be the astronomer to the king, and he made less money than a first-year postdoc. Now, we should keep this in mind when people talk about the sacrifices that we make for a career in astronomy relative to what the sacrifices that people had made in the past. So now if I plot the location of Uranus in the diagram I showed before, that's where it is, and it more or less fits the pattern. It's massive thing, significantly more massive than terrestrial planets. So it seems like it fits what was known with Jupiter and Saturn. The next discovery, though, didn't fit the pattern. And so the discovery of Uranus caused an enormous amount of excitement to ripple through Europe, and teams of European astronomers started searching the skies for other things like Uranus. And so on January 1st, 1801, a Catholic priest in Palermo, Sicily, named Giuseppe Piazzi, discovered another object, which he also at first thought might be a comet. Although, as he observed it 24 times over the next month and a half, he grew more optimistic that it might be something else. In fact, he wrote to his colleague, "I have presented this star as a comet, but owing to its lack of nebulosity and to its motion being so slow and rather uniform, I feel in the heart that it could be something better than a comet, perhaps. However, I should be very careful in passing this conjecture to the public." So this is a sentiment that I actually wish people in my own subfield paid more attention to, because we have a long history of making spectacular announcements in the press only being forced to retract them in a few years. And so I feel like this precedent was something which we should have appreciated more. And in fact, this discovery was also interesting because it was discovered just before the object Sirius moved behind the sun, and so there were very few bits of data to measure its orbit using the traditional techniques. And in fact, in one of his first major achievements, the young Carl Friedrich Gauss invented an entirely new method of calculating orbits, which allowed for the recovery of this object in 6 months after it moved out from behind the sun with unprecedented accuracy and, in fact, ease of calculation. But like I indicated before, this thing does not fit the pattern. It's substantially lower mass than the other close-in planets that were known at the time. And in fact, over the next few years, astronomers discovered several other objects which had very similar properties. So Sirius was the first object which discovered. Vesta, it turns out, was the fourth such object. But people quickly realized that there were more things like this than people were willing to call planets. And in fact, just a few years later 1 year later in 1802, William Herschel comes back on the scene and proposes that these things should be called asteroids. That is, they have a similar appearance to the sun, to individual stars in his most powerful telescope magnification, whereas the rest of the planets he could resolve. So whatever these things were, they were substantially smaller than the known planets, and therefore probably something different. And one of the reasons I showed this diagram was that you can actually pick up this blip of excitement here at the very beginning of the 19th century, just based on the number of times in the documents that Google has indexed, the word planet has been mentioned. Also note that there's this big bump around 1850, which suggests there's something also important going on. And this was astronomers and physicists grappling with what at the time was one of the biggest problems in mathematical physics. That is the orbit of Uranus. So even though Uranus was only discovered in 1781, people were able to go back and find historic observations of it from 50 or even 100 years before. And using those data, people were able to get precise estimates of its orbital properties. And as they observed the orbit going forward in time, they noted that nothing they could do could make the orbit work out. That is, the best predictions using Newton's theories of gravity was unable to predict exactly where Uranus should be. And so this led the astronomical community to the belief that there might be something else out there perturbing the orbit and causing Uranus to deviate from what was expected. And in fact, in 1845, a British astronomer named John Couch Adams, and later at approximately the same time, a French astronomer named Urbain Le Verrier, were engaged in exactly this, calculating the orbit of Uranus and trying to decide what sort of thing could be out there that would be causing these perturbations, which we might be able to tease out as a planet. And in fact, they both deserve some credit, but Urbain Le Verrier actually did the relatively more precise calculation. In fact, once he found an observational astronomer actually willing to go out and look for this object, it was found after just a few hours of searching in Berlin at just about midnight on September 24th, 1846. The planet Neptune was discovered just 1 degree from the place that Urbain Le Verrier had predicted it to be. So at the time, one of the most impressive achievements of the Newton's theory of gravity and taking into account all of the individual perturbations on the solar system. So this object also fits the pattern. It's large, it's massive. It looks like it fits in. Now, people also did the same thing with the orbit of Neptune, and they persuaded themselves, at least some people, that there was something else out there, that Neptune's orbit wasn't behaving as it should. There's got to be something else out there. And so another amateur astronomer, in fact, very wealthy Boston patrician named Percival Lowell, spent his entire fortune building an observatory dedicated to, in one sense, studying Mars, but also to looking for this thing which was causing the perturbation of Neptune's orbit. It turns out he was completely wrong. But on February 18th, 1930, after nearly a year of searching, this man, Clyde Tombaugh, who had recently arrived at the observatory from Kansas, in fact, he had been given the job because of his skill as an astronomical draftsman, he was engaged in a very determined search where he would expose photographs of parts of the night sky and then come back a week or so later and photograph the same part of the night sky. And then he used something called the blink comparator to look for moving objects between these two photographic plates. And in fact, the human eye is an exquisitely tuned machine to tease out these small moving objects. And so after a year and a half of patient work, he was able to identify the movement of that object to there. Now, that's an impressive achievement. Certainly something that I wouldn't have wanted to be in his position. But this object also didn't fit the pattern. It was far away, but it was lower mass than all of the terrestrial planets. Nevertheless, I suspect most of the people in the room, when we learned about the solar system, we learned that there were 9 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and this planet, Pluto. So that's the way it was for me. That's definitely what I learned. But then in 2005, the results of another determined search produced another spectacular discovery. So in 2005, Mike Brown, David Rabinowitz, and Chad Trujillo were engaged in a search using exactly the same technique that Clyde Tombaugh had been using 75 years before, but in a much more sophisticated modern way. So they had computer programs to look for moving things. They didn't have to look for moving things by eye. And so they were able to tease out the movement of this object right here. In fact, they were initially looking for objects that only had substantially larger movements than this, because they initially thought that anything that moved as slowly as this would have to be some sort of false positive due to telescope alignment or atmospheric conditions or something like that. But it turned out that this object, Eris, was smaller in radius, but actually more massive than this planet Pluto. And so the same thing that happened with Ceres in the asteroid belt was happening again, now in the outer solar system. It was okay when there was just one object like that. But if you start to have more, maybe it's showing a pattern. Maybe there's something else important. Maybe that thinking should change. And so you might remember in 2006, the International Astronomical Union held a vote at one of their worldwide gatherings of astronomers. And they asserted that in the solar system, at least, a planet is a celestial body that A, is in orbit around the sun, B, has sufficient mass for its self-gravity to overcome rigid body forces so that it shapes a hydrostatic equilibrium, assumes a shape of a hydrostatic equilibrium, nearly round in shape, and that it's cleared the neighborhood around its orbit. So this definition includes Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, which is what people wanted. But it excludes these other things that people were finding in the outer solar system. And so instead, they called those things dwarf planets. That is, that they met criteria A and B, but not C. So Ceres, Pluto, and Eris are such dwarf planets. And so since 2006, this has been the solar system, the official solar system, that I presume school children today learn. But the story hasn't even ended. In fact, just last year, Mike Brown And another one of his Caltech colleagues suggested that based on this same technique, that if you look at the orbital elements of the small bodies that have been observed in the far outer solar system, they cluster in a specific way. And that one explanation for that clustering is that there exists now a 9th planet in our solar system living somewhere in this box. So if you're interested in hearing more, Mike Brown will be giving the Space Telescope Science Colloquium on March 8th on exactly this object and the evidence that he's gathered to support its existence. So stay tuned. This idea of what is and is not a planet, despite the fact that it's been going on for 2,000 years in our own solar system, is still not settled and is still subject to revision pending new discoveries. Now, while this excitement has been going on in our own solar system, there's also been another revolution. That is the discovery of planets like those in our own solar system orbiting other nearby stars in the galaxy. In fact, since the discovery of the first such object in 1995, there are now thousands of these things known. And the existence of these things has also caused us to reevaluate what is and what is not a planet. But not at the same low mass end that the objects in the solar system has forced us to examine this question. Instead, at the high mass end, that is, things substantially more massive than the most massive planet in our own solar system. In fact, such objects had been theoretically predicted, at least as of 1962. That is, that if you had an object that was forming in the same way that stars form, except it was sufficiently low in mass that its interior would never get hot enough that hydrogen would be fused into helium, then that thing would never glow like a star. It would form, it would have some of the gravitational energy of its formation, and then it would just slowly radiate that energy away. And so Shiv Kumar was the first person to identify this class of object, and he actually suggested they be called black dwarfs. So this was problematic because black dwarfs was already understood to be what happens when you get a white dwarf, that is the degenerate core of a star like the Sun after the outer envelope has been lost to interstellar space, after that object has cooled down. So people already had used black dwarfs for something else, and so instead the word brown dwarf has come to be applied to this particular type of celestial body. And as I indicated before, 1995 was the year the first planet around a star like the Sun in our own galaxy was discovered. It was also an important year for these brown dwarfs. In fact, the first 3 brown dwarfs were all discovered and announced within a few months of the discovery of the first exoplanet. These were Tida 1 and an object called PPL-15, both in the Pleiades, a nearby star cluster, and also an object called Gliese 229b in orbit around the low-mass star called Gliese 229. So these discoveries also were the first observational evidence for this theoretically predicted class of objects that had been suspected to exist for 30 years, but this was the first observational evidence of these things. And this actually had a significant cultural impact, at least in the sense that it made its way into a New Yorker cartoon. This is from the New Yorker in, I believe it was January 10th, 1996. You can tell it's from that era based on the way this Hollywood guy is dressed. Not really so stylish like that anymore. But since that time, approximately 100 such objects as this have been discovered. And it starts to beg the question, in the solar system, we were concerned about things that were not planets down here. But for these systems outside of our solar system, the question is, which of these things up here is a planet, formed like a planet, and which things up here were in fact more along like stars and formed like stars? So I have to give 2 more definitions before we go on. And the first is by consensus. And the second was so controversial that it only made it through an unofficial draft of a working group in 2002. And in fact, very little progress has been made since then. So a star is a celestial body for which self-sustaining fusion provide sufficient energy for the thermal pressure to balance gravity. For solar composition, this includes objects more massive than about 0.075 times the mass of the Sun, or equivalently about 80 times the mass of Jupiter. On the other hand, an exoplanet was proposed to be a celestial body with a true mass below the limiting mass for the thermonuclear fusion of deuterium, which at the time was calculated to be about 13 times the mass of the Jupiter for an object with the same composition as the Sun, that also orbits a star or stellar remnant, no matter how it formed. Part of the reason this definition has been so controversial is that it didn't say anything about formation channel. In fact, if you go back and look at the discussions that were going on at the International Astronomical Union, and since that time by the astronomers who have taken upon themselves to catalog all of the exoplanet discoveries, they need to decide which new discovery belongs in their catalog of exoplanets and which discoveries do not, that are qualitatively different. And so if you read these discussions and if you read the introductions to their papers, they always have to say, for the purposes of this analysis or for the purposes of this catalog, this is what we consider to be a planet. And for the most part, people would very much like to include some sort of criteria on formation, such that things which formed like a planet, say formed in the same way as Jupiter or Saturn in our own solar system, they should count as planets in these things and be included. Whereas the celestial bodies that form like stars, they should be excluded from these catalogs. And everyone always agrees that formation is the key element that would allow that sort of definition. The problem is people despair because it's in general quite difficult to determine, based on the properties of the object, how it formed, especially if that object is very old. And in fact, most of the objects which have been discovered are billions of years old. And after billions of years, most of the evidence that would have given you some insight into that object's formation has disappeared. It has lost the memory of how it formed. And so people have kind of, for the last 10 years or so, despaired of a way forward. How is it that you can better understand what should and should not be a planet, which is intimately related to how planets form and how low-mass stars or brown dwarfs form. So to take a step back to a higher level, it's thought that planets form from the bottom up. That is, if you go to the disk of gas around a recently formed young star, embedded in that gas should be micron-sized dust grains from the interstellar medium. Those are the ultimate fundamental building blocks of planets and people. So when it's said that all we are is stardust, it is actually true. This is one of those cliches which actually has some meaning. So in this early growth phase, these micron-sized dust grains stick via electrostatic forces and coagulate into larger and larger dust grains. This process goes on in some time, and this is actually still an area of astrophysics where there's an enormous amount of both experimental, theoretical, and observational work to be done. But in general, this coagulation happens. We know from our own solar system that asteroids and meteorites that have fallen to the Earth, that this process has to happen because these bigger things get built up from these smaller units. And eventually, in the mid-stage of growth, gravitational attraction starts to be important. So an object has reached a sufficient mass that it starts to sweep up all of the material in an annulus around its area of formation. And as it grows, it becomes more and more effective at this gravitational sweeping. And in fact, the first few things which grow to this size start to dominate their local part of this protoplanetary disk. And they start to grow substantially. And if they grow quickly enough, that is, if they grow to a mass about 10 times the mass of the Earth, in the few million years before that parent protoplanetary disk disappears, then they can start to initiate efficient gas accretion that is not this slow, long time scale accretion, but instead a runaway gas accretion. They can sweep out gaps and annually in their parent protoplanetary disks, basically everything in that region they've eaten up So this was initially theoretically predicted, but now there are famous images of nearby stars like TW Hydrae and HL Tau that have been taken by ALMA, a very new millimeter wave telescope, which sees exactly these features in disks around young stars. So the ultimate upshot here is that the seeds of planets were formed from refractory material, that is, things that are solid at the relevant temperatures, whereas the sun is mostly hydrogen and helium. So planets care about heavy elements, and stars care somewhat about heavy elements, but they're much, much less sensitive to them. And it's thought, in fact, that stars form from the top down. So instead of building up from smaller and smaller particles, sticking them together and growing to larger and larger sizes, it's thought that stars form from some larger scale phenomenon, be it turbulence or gravitational instability or seeded formation from the explosion of another nearby star. You start out with a large-scale perturbation, and it collapses onto itself due to its own gravity. And that's illustrated right here. So this is a theoretical calculation of the formation of a star system. And the forming star like the sun would be right here at the center. And if the disk is sufficiently massive, then this spiral arm pattern is a ubiquitous result of gravity being stronger than the things fighting against gravity. In a disk, it happens to be the Keplerian differential rotation shearing out perturbations, and also just the thermal energy, the temperature of the gas. If those two things aren't powerful enough to hold up the disk against collapse, you end up with these spiral arms and then some sort of fragmentation into, in this case, a low-mass star in orbit around a forming more massive star at the center. So there's numerous ways that you can learn about stellar systems like this, because the stars are intrinsically luminous. We have a much smaller number of ways to actually understand the lower mass planetary systems, because the planets are much fainter. They don't emit a lot of light. They're much more difficult to see directly. So in fact, most of what we know about planets we learn from studying their host stars and indirectly inferring the properties of the planetary system. Two of the historically most successful techniques are relevant to the rest of this story. And the first is this Doppler technique. So this is a diagram of a star and planet system. And so this is exaggerated in the sense that the center of mass is typically inside the star if the object is only as massive as a planet. But the point is that the planet and the star orbit their common center of mass. And because that's true, not only does the planet have an orbit, the host star has an orbit. And the host star moves around in that orbit with a velocity that, for a planet like Jupiter, at about the same distance from its host star as the Earth is from the sun, that's a velocity of about 28.4 meters per second, or about the speed of a NASCAR race, say. So that's the speed that these instruments which we have to be sensitive enough to infer the existence of these planets. And so this is what a cartoon of what actually goes on. So you use a high-resolution spectrograph. You take many high signal-to-noise spectra, and you look for this Doppler wobble of the spectrum of the host star. You look for the absorption lines moving back and forth with a particular frequency and with a particular amplitude. So I've enormously exaggerated the effect such that it could be seen by eye. So this is not a planet. This is a low-mass star orbiting a star like the sun. If I were to have made the same animation with a planet mass object, its movement would have been completely invisible, which makes it that much more of an achievement that these planets have been detected at all. So once you've measured these radial velocities as a function of time, you can fit a model to those data. And this is the type of model that you get and the observables that you can use. So the first thing, this is, say, time on a linear scale on the y-axis and the inferred radial velocity in meters per second on the y-axis. So if the orbit is circular, the curve is a sine curve. It's easy to read off the period, in this case about 4.2 days. Because the orbit is circular, the eccentricity is close to 0. If the eccentricity was significantly non-zero, this curve would be analytically intractable. It would require a numerical calculation to actually to calculate and plot. But you can fit these curves to actually calculate this eccentricity. And then the other observable is this semi-amplitude, basically the size of the oscillation imparted on the star by the orbit of the planet. And from those observables, one can infer a minimum mass of a planetary system using the Doppler technique. Now, this is all relative to the unknown inclination of the system. If the system were inclined such that the plane of the orbit of the planet was perpendicular to the plane of the sky, then all of the orbital motion is along our line of sight. And this radial velocity signal has its largest value. But that inclination is unknown. It could be anything. It could be that instead of seeing a planet, you're seeing a low-mass star that has an orbit such that only a small component of the velocity is projected along the line of sight. So this is a roadblock if you're trying to understand how planet properties or how brown dwarf properties might change as a detailed function of mass. So you need some other information to break this degeneracy. And one way to break this degeneracy is to take advantage of a particular configuration of the orbit where it is so well aligned, just based on chance, that the planet passes between its host star and our line of sight. And the evidence we have for that configuration is a planetary transit. If a planet the size of Jupiter, say, passes in front of a star like the Sun, it dims the light coming from that star by about 1%. It turns out that 1% deviations are not that difficult to measure, even with a telephoto lens comparable to what people use to take pictures at the Super Bowl. You can actually measure the dip of a Jupiter-sized planet transiting in front of a star like the Sun with amateur equipment. And there's an enormous amount of astrophysics that can be done beyond what I'm going to talk about from the transit technique, including the studies of the relative orientation of a planet's orbit and the orientation of its host star's rotation, and also the ability to study the atmosphere of these transiting planets. As far as I'm concerned, the only thing that's important for the purposes of this talk about this transit configuration is that the inclination is known. It's known to be about 90 degrees. And so the mass inferred from the Doppler technique is the true mass of the system. It is not just a minimum mass. The next definition that I need to give is this concept of metallicity. So astronomers were very loose in our terminology in some respects. And so to us, a metal is anything other than hydrogen or helium. It turns out that most of the absorption lines in the spectrum of a star like the Sun are caused by the element iron. And so for historical reasons, we use as a proxy for the overall amount of heavy elements in the atmosphere of a star is the amount of iron in that star. Turns out that is a good approximation. For most stars like the Sun, pretty much all other heavy elements scale with iron. So you're not going too wrong in making that assumption nearby the solar composition. And so this is a logarithmic scale which compares the number density of iron atoms in the Sun's atmosphere relative to the number density of hydrogen atoms compared to the same quantity for a star like the Sun. And so if I say a star has a metallicity of 0, that means it has the same metallicity as the Sun. It has the same ratio of the number of iron atoms to the number of hydrogen atoms. If I were to say that a star had a metallicity of plus 0.3, that would mean that it had twice as many iron atoms relative to hydrogen atoms as the sun. And if I said it had a metallicity of minus 0.3, I'd be saying it had half the number of iron atoms relative to hydrogen atoms in that star's atmosphere. So now perhaps the single most important discovery in terms of understanding giant planet formation that has been made in the history of exoplanets to this point is encapsulated in this diagram right here. That is that the fraction of stars like the sun that have a giant planet like Jupiter is a sensitive function of the metallicity of the host star. If we go to stars that have twice the metallicity as the sun, something like 20% of those stars have a giant planet like Jupiter. Whereas for stars which only have half the metallicity of the sun, that occurrence rate is much smaller, only a few percent. And so initially, it was proposed that planets like Jupiter could be formed both by this bottom-up process, which I've ascribed to planet formation, but also by the same top-down process which led to the formation of stars. And it's this observation that's provided the key piece of evidence that the bottom-up scenario is much more likely to be accurate than the top-down scenario, at least for giant planets and stars like the sun. So if you're interested in knowing, say, what's the most massive thing that can form like a planet and therefore reasonably considered to be a planet, you can follow this plan of attack. So if you're able to identify the mass at which a particular class of celestial bodies stops preferentially orbiting metal-rich stars, that would be the boundary between objects that form bottom-up, like planets, and objects which form top-down, like stars. So what would you have to do that? First thing you'd have to do is collect a sample of transiting giant planets and brown dwarfs with measured masses and host star metallicities. So you'd want, as much as possible, these metallicities to be homogeneous, because there's actually a wide range of ways that people derive these quantities. And it turns out that if you compare one person's estimated metallicity with another person's estimated metallicity, there's usually significant systematic uncertainties. And so it's important to use a homogeneous catalog of stellar metallicities. And in fact, that's not hard. There's been so much interest that's been generated by these exoplanet discoveries that you're spoiled for choice in terms of deciding which catalog of exoplanet properties you want to use. Now, if you want to compare the exoplanets to the brown dwarfs and low-mass stars, you need to do the same thing for a sample of transiting brown dwarfs and low-mass stars with the same measured masses and the same measured host star metallicities. It turns out that's much more challenging. There is no single compilation of these data. And in fact, when I wanted to make this measurement, I had to spend several days combing through the literature, picking out these numbers and putting together a spreadsheet with everything such that I could finally get it all in one place to fully analyze. But then once you have those data, you actually need to do the analysis. And you need to do the analysis in a rigorous, objective way to find the boundary between these two populations. These things that formed like planets that preferentially orbit metal-enriched stars, and these things that formed like stars that don't care about the metallicity of the star that they orbit. So this is a plot of those data. Here's the mass of the secondary in the system, that is the planet, the brown dwarf, or the low-mass star, on a log scale in Jupiter masses on the x-axis, and this metallicity with iron as a proxy on the y-axis. So you might be tempted to draw lines in this diagram just based on your eye. But that's one of the things which has led astronomers astray in the past. And so I took a qualitatively different approach. What I did was I applied 3 different classes of unsupervised learning algorithms to these data. I used a bottom-up classification algorithm that starts out putting each object in its own class, determining the dissimilarity metric between each object, and then slowly moving up through effectively a tree, matching together objects that had the smallest dissimilarity, and continuing until all the objects have been classified in one of two classes. I also used a top-down approach called k-means, where I assert that there are two classes of objects in this diagram, and then the computer tries to find which centroid in this space minimizes the within-group dissimilarity. And then the third paradigm is one can specify in advance that the clusters have to be modeled by a particular functional form. And then you can find the functional form, the parameters of the functional form, which do that same thing. They minimize the within-group mutual dissimilarity. And so for the purposes of this calculation, I used a Gaussian because there's very efficient computational implementations of that. And this is the result. For all three classification algorithms, everything on this side of this gray bar is classified together. It's the low-mass things which preferentially orbit metal-enriched stars, so I call that the planet class. And everything to the right of this gray bar is classified with the higher mass objects which don't care about the metallicity of their host star. The colored ellipses in the background are the Gaussian models that best describe this data set. And then in this no man's land, there are some objects there's some disagreement between the different algorithms as to which way they should be classified. So everything below 4 Jupiter masses is confidently associated with the planet class, and everything in excess of 10 Jupiter masses is confidently associated with the brown dwarf or stellar class. And this is actually somewhat lower than the canonical 13 or so Jupiter masses which people have used to classify these things just based on this arbitrary definition of whether or not they are ever capable of fusing deuterium in their cores. It turns out that this clustering in composition and mass space is also a local minimum in the occurrence rate of objects of this type. Here on the x-axis, I plotted the minimum mass here because I've been forced to use objects that have only been detected with the Doppler technique, so I don't know the inclination. And basically the number density is a function of minimum mass on the y-axis. This is the same gray area from before. It occurs in exactly the same place. And it occurs in a valley. There are relatively more low-mass stars and brown dwarfs. There are relatively more low-mass but still giant planets, and relatively few massive giant planets or low-mass brown dwarfs. Now you might quibble with the clustering calculation and say, well, part of what you saw is contingent just on the observed number density of these things or the discoveries of these things. Maybe there's some bias. It turns out that in this range of mass, radius is not a strong function of mass. And all of these objects have been discovered with the transit technique. The only thing that matters for the transit technique is the ratio of the radius of the host star to the radius of the secondary companion. All of the host stars in the sample are stars like the sun, so they all have approximately the same radius. All of the secondaries have approximately the same radius as Jupiter. And so the occurrence rate of these things is insensitive to the selection effects that went into the surveys which discovered 99% of these objects. But still, you can do a similar analysis which does not at all rely on the occurrence rate. And so you can just say, at what mass does the moving median of the metallicity move below the minimum metallicity observed in the giant planet region? So this is the same plot as before, using the same data set as I showed on the first slide, with mass on a log scale on the y-axis, this moving median iron metallicity on the y-axis. And there's some bumps and wiggles, but the minimum occurs here at just slightly more or slightly less than 1 Jupiter mass. And the moving median moves below that at exactly the same point, at this same 10 Jupiter masses. So completely independent of the occurrence rate of these objects, there's a signal simply in the composition of their host stars. So this requires the statistical analysis of what in truth is a relatively small sample, although I would argue that there's nothing you can do to make this signal go away. But in just a few years, there will be a large enough sample to make a completely definitive measurement of this property. So a few years ago, the European Space Agency launched a satellite called Gaia. And Gaia is engaged in doing more or less exactly the same thing that William Herschel was engaged in when he was looking for the planet Uranus, looking for the astrometric wobble of stars in our own galaxy. And not just to find binary stars, but also to measure the distances to nearby stars. It turns out that if you're interested in precisely measuring the distances to nearby stars, you need to worry a lot about the occurrence rate and properties of low-mass stars, brown dwarfs, and giant planets with orbital periods proportional to the mission lifetime. Because if your model doesn't include the ability to discover those things, you're going to be unable to actually use these measurements to calculate the trigonometric parallax and therefore the distance to these stars, which is the main reason for this mission's existence. And in fact, even though the sample that I presented had just more than 100 objects, this Gaia mission in the next 5 years is going to discover thousands of objects in this range of mass and orbital period around stars like the Sun. These are all going to be nearby stars. They're all going to be relatively bright. It's not going to be that difficult to make this metallicity measurement for this sample. And my prediction is that when that measurement is made, the objects that Gaia discovers that have masses less than about 10 Jupiter masses are going to preferentially orbit metal-enriched stars, whereas the objects it discovers that have masses in excess of 10 Jupiter masses are going to orbit stars randomly sampled from the metallicity distribution of stars nearby to the Sun. And so my conclusion is that for Sun-like host stars, the planet formation process does not seem to produce planets more massive than about 4 to 10 Jupiter masses. Planets form from the bottom up. They prefer metal-enriched stars. And it seems like these objects stop preferring metal-enriched stars once their individual masses grow in excess of 10 Jupiter masses. This top-down star formation process produces objects independent of the metallicity of the host star. And it seems like that process is dominant for objects more massive than about 10 Jupiter masses, or at least the subject of the limitations of the sample that I studied, that is, binary companions to Sun-like stars. I would argue that it now is safe to include this formation channel idea into the definition of an exoplanet, which has been a goal long sought, both by exoplanet classifiers and planet formation theorists. And moreover, there will be a definitive measurement of my inference based on a small sample in just 5 years in the thousands of giant planet, brown dwarf, and low-mass star binary systems that Gaia will discover. Thank you. Tim.
The definition is in most of them focus on the things orbiting larger bodies, which you can have brown dwarfs that are isolated. And I thought with microlensing, if there are exoplanets that have been injected, let's say,
So there is a controversial claim. So Tim's question had to do with the occurrence rate of objects of a similar mass that do not orbit stars like the Sun, that are just freely floating through space. And so there has been a claim from microlensing surveys that is looking at the gravitational focusing of light by point sources between us and the galactic center, where the brightening of the background star that's being lensed is so short that the only way to explain it is by something that's very low mass. And it's been argued that the number of these such events that have been seen relies on there being as many free-floating planets approximately the same mass as Jupiter as there is stars like the Sun, or stars in general. And so there's some debate about the statistics in that claim. And that claim could also be explained just by distant giant planets. It doesn't have to be completely free-floating things. So it's quite possible that more micro-lensing data will either lead to better statistics, which might cause the signal to go away, or it might lead to better statistics in terms of the ability to identify the actual primary in the system to know whether there are these things are free-floating or just have orbits that are quite far from their host star. So the things that I presented I admit, is limited to things in orbit around stars like the Sun. But in some ways, that's also, it seems like based on our own experience in the solar system, being in orbit around another star seems to be some necessary criteria, necessary requirement for planethood. But that's something I'm agnostic to. Ultimately, my interest was trying to understand the planet formation process and having potentially this new fact that whatever the planet formation process is in detail, it doesn't seem to make things more massive than about 4 to 10 Jupiter masses.
So turning this around and saying, now rather than look at planets in definition based on formation schemes, multiplicity in stars, so you make a more massive star, and those could also have multiple companions, some forming in a more traditional collapsing, whatever it comes to turbulence, but also forming more planet-like state. Is there any indication that you have for like much more massive host stars that should be planets, but they just accrete
Yeah.
mass?
So the question has to do ultimately with the mass ratio. Is this observation just telling us what the mass ratio of companions formed in this way is, or is it telling us something about the intrinsic absolute mass? And so because I focused this analysis simply on the stars like the Sun, because that's where selection effects allow us to find planets, and so that's basically the only game in town for these transiting systems that for the time being gives a precise measurement of mass, which permits the measurement that I made. I focused on stars like the Sun. But this is also something that Gaia is going to be fantastic for, because the problems with finding planets around massive stars with either the Doppler technique or the transit technique are not the kind of thing that are going to affect Gaia. So this prediction for the Gaia yield, some subset of these are going to be around 2 or even 3 solar mass stars. So we will get more leverage on whether or not this effect is just related to the mass ratio, or whether there is some intrinsic scale of the planet formation process. Jonathan?
So you're drawing on information channels based on a sample of orbiting planets that are virtually very close to their host stars. Whereas my understanding of Gaia is it's virtually associated with population planets that are cheaper. So why do you claim that you can draw the inference with the same population?
Yeah, so that's also another caveat, is that it's true that most planets are far from their host star, whereas this analysis was restricted to planets relatively close to their host stars because that's the only type of planet that typically transits. So that's another limitation. But that's another limitation which will be removed by Gaia, because the things that Gaia is going to find are going to be much longer period. Most of these objects are going to have orbital periods between 1 and 4 years. So if my scenario is accurate, then Gaia should see the same thing. And if my scenario is restricted just to the closest in things, then Gaia potentially will see something different. But we will know in 5 years or so.
I have a question about one of your conclusions. I think it's the second one. I wonder if you can conclude on. So it seems overstated to me, and I want to express something slightly different. I wonder if like 1 in 4 or less than 10 Jupiter masses, would that invalidate the claim? Would you say 1 in 4 is essentially 0, or it is essentially too big for me to believe this claim?
I'm sorry. So the data that I presented is what it is. If you look at stars like the Sun that have Jupiter-sized things over a range of masses, the objects that are below 4 Jupiter masses preferentially prefer metal-rich stars, which we think tells us that they formed like planets, whereas the things more massive than that don't prefer metal-enriched stars. So this again, ultimately the caveat is what I'm talking about is restricted to things in orbit around stars like the sun. If we're talking about free-floating things, then
No, let's not worry about free-floating things. I give you that caveat, but I'm trying to drill down on, it seems that you partition things into two groups.
uh-huh.
And now you're going to evaluate the mass. 10 Jupiter masses is where the two groups are best separated. But it doesn't mean that there isn't a tail of the star formation process below 10 Jupiter masses. And I ask, how much of the tail is less than 10 Jupiter masses?
Okay. So it is possible that such a tail exists because this is a statistical calculation in the sense it's not deterministic. But it is true that there are very few such things, right? There are very few such things on either side.
Is it 75%? In which case I don't care. If it's 10%, wow,
Okay.
that's pretty good.
So I don't think I have enough statistics right now to make that claim, is to be able to say what fraction could be there that formed like stars. But I have some hope that if there are now thousands of objects instead of just 121, that it might be possible to dig deeper into that question.
Thanks.
Let's thank the speaker.